Well, welcome to class today. We are going to start today on a topic that I feel like is one of the most central to the idea of circuits analysis. And this topic that we're covering today is often given the name nodal analysis. The reason it's given the name nodal analysis is that what we do, maybe this is not surprising when we do nodal analysis, is we analyze all the nodes in a circuit. Okay? What do we mean by analyze the nodes? Like I have written up here, nodal analysis is a more thorough usage of KCL. What do I mean by KCL? All right, Kirchhoff's current law, right? So Kirchhoff's current law says what? The sum, sometimes the people say the algebraic sum, of all of the currents entering or exiting a node. You have to choose which one you're going to define as positive, right? All the currents entering or exiting a node must sum to 0. Okay? And so what we're going to do is we're going to start viewing circuits in today's lecture as being sort of this collection of nodes where we can use the information that we have for each node about all the currents that would flow into and out of each one of those nodes. And what will typically arise out of the types of circuits that we analyze in here, what will typically arise is some kind of a system of equations, the solution of which is generally going to be the voltages that were associated with that circuit that will be tending to drive current through the different resistances that are part of that circuit. Okay, so that's kind of the big overview of what we're going to do, is use a bunch of different nodal equations for each one of the nodes in a circuit, and then take all those and put them together. It'll result in a mathematical system of equations, and we'll solve that to figure out all the different pieces that we don't know currently in the circuit. The voltages and currents typically are what we're going to be solving for in these things. So anyway, I think probably the thing to do is to go ahead and get into this and describe the steps of doing nodal analysis, and then we'll do a few examples. Okay? So we'll start here. Nodal analysis steps. Item 1 should not be surprising to anybody. Okay? Item 1 says identify the nodes. Okay? So why don't we go ahead and do that on this little circuit, because what I'm going to do is as I go through each one of these steps, I'm actually going to do it on this circuit so you can see what that looks like. Okay? So let me start by identifying this node down here. Right? Again, you stick a highlighter on there, and you try to take that highlighter as far as you can in every direction along just wires until you hit some kind of a circuit component, right? And everything you color as you do that is a node, right? So I just identified all that stuff down there as a node, and I have it colored green, okay? Let me put one up here as well. Okay, here's another node up here. Okay, go as far as I can in every direction until I hit a circuit element. There's another node right here. Okay, and then there's a fourth node here. All right, and that just doing that much right there helps us to at least see where all the nodes are, so that we can move on to the next steps in the analysis. Okay? So there's actually kind of a very important step that is done right here that you probably want to do before you go to anything else, and that is choose one of your nodes to be a ground node. All right? Or sometimes this is called a reference node in some of the literature that you might read. Okay? This is essentially the node that we're going to kind of pretend the voltage at that node, the absolute voltage at that node, is 0. Technically, it doesn't have to be. All we're saying is that we're going to pretend like it's 0 relative to all the other voltages that are in the circuit. Okay? So that when we say there's a voltage at a particular location, we don't necessarily always have to say relative to this node. We can always just sort of assume we mean that's a voltage relative to the reference voltage or reference node voltage, right? And we're essentially going to assume that that reference voltage is 0. Okay? Here's how I typically will identify which one is the ground node is I'll go ahead and add a little thing on here. I'm going to do it in red so you can see it. You don't have to do it in red, but I'm going to add a little symbol on there, on that node down there that I'm choosing as my ground node. It's colored green. I'm choosing that as my ground node, and I add a little symbol that is a ground symbol. And that way I know that all of my voltages that I'm defining in the circuit are going to be relative to that node. Okay? Next, step 3 says define voltages for each node relative to the ground node. Okay? You don't have to be super fancy with this. Typically what I will do is I'll just say, V with a subscript on it. Kind of identify nodes and sort of number them, right? So I might say V1, which kind of implies that yellow node up there I'm saying is node 1, right? I'll call the voltage here on this node, this blue one right here, V2. And on the purple one over there, I'll call that V3. Okay, so I've now defined 3 different voltages relative to my ground node, right? And that's all you really have to do with step 3. Step 4 is where most of the work happens, right? Step 4 is where we write Kirchhoff's current law equations, and you typically will do this in terms of the voltages you just defined, but you're going to write those Kirchhoff's current law equations for each one of the nodes except the ground node. All right, so we're going to do for this one 3 Kirchhoff's current law equations because we have 3 nodes that are not the ground node. Okay, so may as well just start with the first one and start working through it. Okay, so the first one is the yellow node, right? So maybe I'll put right here node 1. And just to be totally clear there, I'll color it like that. What would Kirchhoff's current law equations look like for that yellow node? Okay. Let me ask you this. How much current would flow from that yellow node to the blue node? Right? Say a little current coming from the yellow to the blue. Okay. I heard someone say V1 minus V2. But we're talking current here, right? That's what I just defined right there is a voltage difference between those 2 nodes. But I also know a resistance value between those 2 nodes. So Ohm's law says the amount of current that flows would be V1 minus V2 over 3 ohms for that one. Right? So I just took care of a current that flows from the yellow node to the blue node. Would you call that a current that's entering the node or a current that's leaving the node? Okay, leaving or exiting, right? That's a current that's moving out of that node. And I've taken that to be a positive value here. Okay, when you do these equations, you have to make sure you are consistent about that. Are you taking an exiting current to be a positive, or are you taking an entering current to be a positive? What I basically did with this first term is I chose to make exiting currents positive, right? Because that one's would be an exiting current, and I made it positive. So now I have to match that with all my other terms in my equation. Okay, now what would the current be flowing from the yellow node to the purple node? Yep, based on the same type of logic we just did for this one, you would do V1 minus V3 over 1 ohm. Okay, so far so good. Okay, now what other currents might flow into or out of node 1? Okay, you have that 2 amp current source, and so that makes it very easy to know how much current flows on that leg, right, out of that node. It's just 2 amps. So I say plus 2 amps. Are those all the paths into and out of node 1? That's it. So we say that's going to be 0. Not a bad idea before you move on to the next step. Can you solve anything with this one? with this equation yet? Okay, how many unknowns in that one equation? 3 unknowns in that equation. Probably not going to be able to solve it with just one equation, right? So, but it's always a good idea to at least look at that and see, is there something you can do with that one equation? Okay, so we just did the first of the 3 nodes for step 4 right here. What do you want to do next? Okay, node 2, nod 2. Okay, and I'll color that like this. So we're about to do node 2. All right, and let's again take exiting to be positive. Okay, I would say that there would be a current that exits node 2 going to the left toward the yellow node, right, toward node 1. It exits, and the value of that current is going to be equal to V2 minus V1 over 3 ohms. See how all it is essentially just that first term that I had for node 1, but negated, right? That would make sense, right? Okay, so that's how much leaves the blue node going toward the yellow node. Then what? Okay, you could do just V2 over 4 ohms. And I chose to put a plus sign right there because V2 is, a voltage, positive is kind of assumed, right? Positive voltage relative to the green node, which is assumed to be 0, right? So that's kind of like saying V2 minus 0 over 4 ohms would be the amount of current flowing from this little bluish node down toward the green one. Okay? Where else do I have current flowing into or out of the bluish node? Okay? I have 5 amps that's exiting that blue node going toward the purple one, right? So that would be plus 5 amps. Okay? Anything else for that node? All right. Looks like those are all the different paths that we would have for current to enter or exit the blue node. So we'll set that equal to 0. Then what? Okay. Let's go on to node 3. Okay. Node 3 is colored purple. All right, which one do you want to do first for node 3? Okay. You have the 5 amp, okay, so you certainly could do that if you want to. It's entering. If we're taking exiting to be positive, what do I do with that value? Okay, negative 5 amps. Then what? Okay, plus V3 over 6 ohms. Okay, what else? Okay, plus V3 minus V1 over 1 ohm. All right, any other places where current could enter or exit the purple node? Nope. All right, now that we have written all those things down, let's take stock. Okay, how many unknowns do I have total? They are V1, V2, V3, right? So there are 3 unknowns. They are V1, V2, and V3. How many equations did I write? 3. So things are looking promising, right? We might be able to get to the bottom of this. Step 5 says, solve the resulting system of equations for voltages. Now, let me expand that just a little bit. Typically, they will be voltages that you will be solving for. We will see another couple of examples in today's lecture where there might be other types of values, specifically currents, that you might also solve for some of these circuits that get a little bit more complicated. Okay, save that for when I show it to you in an example that's coming up. Okay, but in order to solve this resulting system of equations, there's a few options for that. You certainly have all of your algebra tools that you might remember from algebra classes. You know, most of you probably don't just love crunching numbers like that. So a lot of you have calculators that will do systems of equations. Those calculators you have that do systems of equations, what format are they looking for you to put information into them in? Typically what they want is a coefficient that is multiplied by the first of your set of variables that you are trying to solve for. But it wants the coefficient, right, in the first equation. And then the coefficient of the second one, right? So you want basically to boil this thing down to where each of your variables has just one coefficient of that variable. So I propose that we take these three equations and rewrite them a little bit so that we make them calculator friendly. Okay, does that make sense? So let me give myself a little bit of space here to do that for node 1. What I want to do is isolate first all of the coefficients that would be part of V1, right? So if you look at this, since V1 and V2 both have a common denominator, I could split it apart into V1 over 3 ohms minus V2 over 3 ohms. For now, I'll do that and only consider the V1 part of that. And if I do that, then what I end up with as the coefficient is basically 1 over 3 ohms times V1. But you'll notice I didn't quite write V1 just yet. Why is that, you think? Okay, I've also got the V1 that's over here in this term. I can do the same thing with that one and split that apart into a V1 over 1 ohm minus V3 over 1 ohm, right? Once I do that, I can recollect the 1 over 1 ohm with the 1 over 3 ohms over here like this. And that becomes the entire coefficient of the V1 variable. Follow me with that? What about V2? Okay, there is only one location where V2 exists, and it has a coefficient essentially of minus 1 over 3 ohms. Right? But that takes care of all what we need for V2. Okay, so I'll put in V2 there. What next? Okay, V3 kind of works similarly. We say minus 1 over 1 ohm. V3. What do I do with my 2 amps? It's just a constant. Most of your calculators have that set up to where it wants that actually on the other side of the equation, right? It wants you to put that over on the kind of after the equal sign. So what do? Equals 2 amps, negative 2 amps. Okay? Good job. All right, now what we need to do is node 2. Do the same thing here and give myself a little bit of space. Okay, I'll go a little faster with this one because I'm sure y'all kind of followed what I did with that one. So with this one, what we'll have is for V1, I will have minus 1 over 3 ohms. You can, if you would like, put that in parentheses if you really want to emphasize the kind of nature of its purpose as being like a coefficient of V1. What else do I have here? Plus 1 over 3 ohms plus 1 over 4 ohms, V2, okay. Do I have a V3? Okay, tell you what I'm going to do just to really make this pop. I don't, but I'm still going to put in here plus 0 V3. And I'll do it a different color to really make it stand out that, you know, you can do that, right? Okay, what do I put on the after the equal sign? Negative 5 amps. All right. Okay, last one. We will do, let's do minus 1 over 1 ohm V1 plus 0 V2 plus 1 over 6 ohms plus 1 over 1 ohm V3. Okay. This is all going to be equal to 5 amps. Okay. And so what we have with these three lines right here, right? The one that we started off with right here, this one right here, and this one right here, what we have is a system of 3 equations in 3 unknowns, and your calculators will typically be able to solve that without issue. Okay, here's how you would put it in. First, in this calculator at least, you go to the equation mode. And in equation mode, we're going to choose the 3x3 system, which is option 2 right here. By the way, that option gives you a clue as to the format that it's looking for that equation to be in, right? Coefficient times x plus coefficient times y plus coefficient times z equals constant that's not multiplied by one of your variables, right? That's the format it wants it to be in. So if you ever forget that, you can always look back at that screen right there. Okay, so right here we'll do 1 over 3 plus 1 over 1. Okay, for my first entry. For my second entry, I will do negative 1 over 3. Right? The next entry, I'll do negative 1. And then for the last one, I'll do negative 2. Okay, so I just basically put in each of the coefficients that I needed from that first equation. The next equation, I'll do minus 1 over 3. I will do 1 over 3 plus 1 over 4. Okay, 0 and negative 5. We come down here, we do minus 1. We'll do 0. We'll do 1 over 6. Whoops, what did I do there? I missed my 1 over 1, right? So I do 1 over 6 plus 1. Okay, and then lastly, I do 5 for the 5 amps. Okay, and it will start reporting answers. What does it mean by X? Okay, it means the first of the variables that I had in my calculator, right? So that means that I write down V1 is equal to minus 2 volts. V2 is minus 9.714 volts. And V3, you hit equal sign one more time to see that one. You have 2.571 volts. Whoop. I kind of meant to label it properly there too. Okay, and so these are the solutions. All right, so now you've seen your first nodal analysis. Cool, right? Why do we care about this nodal analysis? Let me tell you some things. So first of all, you may have run across, or maybe not yet, but you may have run across certain circuits where it was impossible for you to use the technique of finding an overall equivalent resistance to figure out like a source current or something like that, and then, then use other techniques like voltage division, current division, those kinds of things to move through the rest of the circuit and find all the unknown stuff, right? That was sort of, that's a quick description of the technique that you were taught in your freshman year, right? That technique will fail sometimes, okay? Because it's not always possible for you to come up with an equivalent resistance of a circuit. Look at this circuit. Well, you can't, it's not on the screen right now. How would you go about finding an equivalent resistance of this circuit? Yeah, you kind of can't, right? And so some of the techniques you have learned are really good for certain kinds of common circuits, right? So it's not like it's bad stuff to know, but those techniques do break down. And so having something you can go to that doesn't break down in the face of certain types of circuits is helpful. And so today we're learning nodal, and next time we will learn mesh. These are essentially the duals of each other, two different ways of doing this kind of a technique, but they will solve a lot of circuits that other techniques will not. Okay, so this is a powerful tool and technique. Let me give you a couple of tips here. 3 tips. One of them I already said, but I'm going to say it again. Okay, don't sum the ground node. Okay, when you actually look at a circuit like this, it will always have one more node than you have independent voltages, right? Or kind of independent parameters in order for you to be able to specify those. In other words, let me say it this way. This will be a better way to say it. Once you have done Kirchhoff's current law for all but one of your nodes in a circuit, Kirchhoff's current law is implied for the last one by all of the relationships that you already used, right? Because there's no other place for current to go. So if current was conserved in all but one of your nodes, you have already used all the information that you can using Kirchhoff's current law at that point. If you try to do Kirchhoff's current law on the last node, then what happens is you don't come up with an equation that is independent of the ones that you already came up with. Okay? So this is a quick and easy way to say, don't get yourself in trouble with that. Just decide, I'm not going to sum currents on the ground node. I'm going to do it on all my other nodes. Okay? Tip 2, always carry and check units. Can you add voltages to currents? Not without doing something else to them, right? It doesn't make any physical sense to try to add a voltage to a current, right? You can have other weird things that happen too, where you come up with parameters that don't even really make sense. If you're not carrying your units, it's very easy for you to get into these equations and all of a sudden do something that makes no sense physically. But you'll notice that what I did is I carried all of my ohms through that equation. We'll say voltage over ohms gives us what? Volts per ohm is amps. Okay? So it makes sense here how I'm summing these things up, that all of those parameters, once I multiply by the 1 over ohms, all those parameters wind up being in amperes, so I can add them all up. Okay? Okay, third tip that I'm going to give you here is defining your positive current direction as exiting will make your equations clean and easy to write. Why is that? Those are my tips. But why is it that defining the exiting direction as being positive, why is it that that tends to make your equations cleaner and easier to write, you think? Okay, think about what we just did with this problem. Anytime you have current exiting one of these nodes, it means you take the voltage at the node that you are evaluating and subtract some other node. So you can essentially start each one of your terms always with the voltage I have here at this node. So if you're doing node 2, you start each one of these voltage differences with the voltage at node 2, right? And then you subtract one of the other ones. So it allows you to get into a pattern and a rhythm of how you write your equations, and that a lot of times will help you not make mistakes. Okay, so these are my 3 tips. The first 2 are kind of non-negotiable. The third one is sort of a, hey, you might see a little bit of easier time doing this using that third tip. Any questions yet so far about this nodal analysis technique? None? All right, let's do another example then. All right, and the point of this example is, what do we do if we've got voltage sources present in the circuit? You'll notice the first one that I did had nothing but current sources. This one has voltage sources present, okay? This makes things just a little bit more tricky because when you have a voltage source in the circuit, it doesn't imply by itself, it does not imply anything about how much current flows through the voltage source. That number can be any amount. Okay, I shouldn't really say that. That number is set by the rest of the circuit, right? It's not set locally right there by the behavior of the voltage source, right? So the amount of current that flows through a voltage source is essentially unknown until you start doing the analysis of the whole circuit. Okay, so that's what makes voltage sources a little bit more tricky. Now, I will say that there's kind of the way that you would go forward with this, not really knowing any kind of a trick, and then in a second I'm going to show you a little trick on how to make this a little bit easier. Okay, so let me show you the kind of the way that we would stumble forward if we didn't know something that would make our lives just a little bit easier. Okay, we'll just follow our steps. What was our step 1? Okay, identify a ground node. So let me just do that kind of similar like I did last time, right? We'll say this is the ground node down here. So let me color that ground node kind of like I did on the last one. Okay. Let me color my other nodes too, because actually, I guess my step 1 was to identify all the nodes, right? So I flipped those first 2 steps. I identified a ground node, but you get my point. Let me identify all my other nodes as well. I've got one up there. I've got one here in the middle. And now I've got one that goes up and around here. Okay. Now, before we even, because once we've done this and we've identified the ground node, what was our next step? Define voltages for each node relative to the ground node. Okay, so let me do that. Where are my voltages? Kind of do like we did last time, right? V1, V2, V3. Okay. What's my next step after that? Write KCL equations in terms of voltages for each node except the ground node. Okay, so let's try to start doing that for node 1. Okay, One term of node 1 is pretty easy, right? V1 over 4 kiloohms is the amount of current that exits the yellow node going down to the green node. Agree with that? Okay. Here's another one that's not too hard. Plus V1 minus V3 over 2 kiloohms. Okay. Do those two terms that I've put up there so far, do those take care of all of the paths into and out of the yellow node? Okay. No, they don't. Where's my other path? Through the 50-volt source. Do I know how much current flows through the 50-volt source? Okay. Just to be, totally, over the top clear about this, can I do anything where I take like V1 minus V2 and multiply it by something to figure out my current through that source? No, I can't do that because it's not a resistor, right? It's not something where I know what that voltage-current relationship is. The voltage across that element versus the current through it are independent for a source. Okay? So what might I have to do then? Well, I'll tell you, this is the way you stumble forward not knowing what to do. Let's just make a new variable. Does that sound like a plan? Okay? Let me just call another variable here, I1. Okay? That is acknowledging that there is a current through that source. I just don't know what it is. Right? Once I call that I1, can I continue with my equation here? I can, right? I basically say these were all exiting, plus now I1 is also exiting. Okay? Anything else? That's all the paths now, it looks like, for that first node. All right, now what? Okay, can I move on to node 2? Okay, node 2 is the blue one. I just said I had I1 leaving node 1 going to node 2. That means I have what coming to node 2 from node 1? I1, right? So you would count that, if we're taking everything as exiting, you would count that as a negative I1, right? Because it's actually an I1 entering the blue node. So that means it's a negative I1 exiting the blue node. Okay? So that's one of my currents coming into the blue node. What else? Okay? I have V2 minus V3 over 1 kiloohm. Okay? Any other paths? Okay, I have V2 over 3 kiloohms for the path coming from the blue down to the green. Right? So that would be plus V2 over 3 kiloohms. Now are all my paths accounted for? Okay, so I set this equal to 0, and I move on to node 3. Okay, for node 3, I guess I'll start with V3 minus V1 over 2 kiloohms for a current that's leaving node 3 over to the yellow node. Then I'm going to add to that V3 minus V2 over 1 kiloohm Then what? All right. Now I've got this 20 volt source feeding V3, right? So what do I do with that? All right. If I want to follow the kind of technique I did last time, maybe I could define a current flowing up through this way and call that I2. Okay. How do I account for I2 in this equation? Minus I2. And this is equal to 0. Now, some of you are probably feeling a little uncomfortable with this set of equations up here. Why is that? Yeah, so we have V1, V2, and V3 are unknowns, plus we also have I1 and I2 as two new unknowns that we introduced in the process of trying to describe these, all these currents. So now we have 5 unknowns, and only 3 equations are written. Does that make you unhappy? It wouldn't surprise me if it did. Let me help you out a little bit, though. Are there any other relationships that we have left dangling that we haven't used, that we could maybe bring in here? In other words, let me say it this way. There, it looks to me like there's information available about our voltage sources, right? Nowhere on here did I ever use 50 volts or 20 volts. How do we use that information? Because it probably matters, right? It should come into the solution of this problem, because how much voltage and current happens everywhere in the circuit is going to be a function of what those values are. So it should show up in there somewhere. How does it show up? Okay. Well, some of you are like trying to come up with a law. Let me just say the definition of voltage is always that voltage is across 2 things. And what does a voltage source do? It holds that voltage across 2 things at some value regardless of whatever else happens at the rest of the circuit. Okay? What this does for us is it allows us maybe a couple of extra equations. So let me put over here, these are nodal equations. I'm going to slide this down just a little bit. These are nodal equations. Okay? But we also have some extra ones. What are our extra equations? How about V2 minus V1 equals 50 volts, because that's what that voltage source does. It holds V2 relative to V1 at 50 volts. So if you take V2 and subtract V1, you will have the value of that voltage. Okay? What other extra equation might I be able to write? All right. I think I may have heard someone say this one. V3, oops, V3. Now I could say, if I really wanted to be clear, V3 minus 0 volts equals 20 volts. Right? Because ground is at 0 volts. Okay? Or I could just say V3 is equal to 20 volts. Now, how does the outlook appear on all of these equations? Okay? Probably a little bit less daunting. What happens if I come in here and I replace everywhere I have a V3, I say that's no longer V3, that's 20 volts. Or I can go down here and say everywhere I've got this V3, that's 20 volts. Or this V3 down here, this is 20 volts. Okay? So far, so good. But I've still got these I's in here that, you know, how do we go about dealing with those? Okay, I'll give you a little clue here. Could I take this negative I1 and move it to the other side of this equation? Like this. Are those two equations equivalent? The one that I had and the one that I just made with it. What does that do for me? That makes a substitution very easy by taking this I and plugging it in right there. Right? So let's see what this equation becomes once I plug that I in. I'm going to have a V1 over 4 kiloohms plus V1 minus 20 volts over 2 kiloohms. All right. Then lastly, I have to put in everything that was to the left of this equation sign right here, right, or that equal sign. So then I'm going to have plus V2 minus 20 volts, okay, over 1 kiloohm plus V2 over 3 kiloohms what else? Equals 0. So essentially what I did is everything that was in these blue parentheses right here, I just moved that right here, doing that substitution. All right. Does anyone have more hope glimmering now? Okay, let me show you why maybe it's a good idea that you have hope glimmering. Look at this blue equation that I just wrote and the fact that you might be able to join that up with that equation right there. How many equations? 2. How many unknowns? In those 2 equations, there are only 2 unknowns, V1 and V2. Right? That means you can solve those, and they are independent equations, I should say that. They are independent equations, and because they are, and you have 2 of them, you can solve for V1 and V2. Okay? Now, I already showed you an example of how to do that. If you're okay with it, I'll just report to you what these answers are of, you know, plugging those 2 things in. Okay? So, the solution for V1 and V2 is just going to end up being negative 17.6 volts for V1 and V2 is just going to be 32.4 volts. And that's what you can get so far out of that system of 2 by 2. Okay? What else can we do now? Okay, at this point, we have found all the node voltages relative to that ground, right? Because that's what the instructions were up here. It says define a ground node and find all other node voltages relative to that ground. Okay, we're done because we have V3 we already found with that equation. It's 20 volts, right? But is there any other information that might be interesting? You might be interested in what I1 and I2 are, right? How do you get those? Okay, I won't do it. You all are good at algebra. I think it would bore you if I did it. But if you wanted to, you could go in and plug in all of your voltages back into these equations, right? You could actually pick either one of these two equations right here, plug in the voltages you now know, and find I1. You do the same thing down here, plug in all your voltages, and find I2 if you're curious how much current is flowing through those voltage sources. Okay? I'm going to give you one of them, and if you are curious about the other one, I'll let you find it. Okay? I2 ends up being 6.4 milliamps.
So when we plug this into our calculator, do we need to convert it to ohms to ohms?
Great question, okay? I did this one in terms of kiloohms, and the question was, when you do this in your calculator, is it important to convert your kiloohms into ohms? Okay? I recommend it to do that. Having said that, though, look at the equation carefully, right? If you have this V1 and V2 and V1 equal 50 volts, that doesn't have any kiloohms in it, and that's one of the two equations you were going to use, right? So that one, obviously, there's no need to convert anything already. But what about down here? Would you say that it would be possible for me to divide through everything in the blue equation? Well, let's say instead of dividing through, let's say I multiply by 1,000 through that whole equation. What would that do? Would it change anything as far as the results of the equation? If you take an entire equation and multiply by a constant on both sides, does it change what the results for the variables are going to be? No. So that won't change anything as far as the results of the variables. But doing that allows you to look at this and say, I've got 1 over 4,000, let's say, on the first term, but now I'm multiplying through by 1,000. Okay? So the answer to your question is, for that equation, it's not that important that you have actually do those conversions for kiloohms. Having said that, I still recommend that you do it so that you're in the habit. But the result will come out correctly for that pair of equations if you don't. Yes?
On node 1, how can everything be exiting
Okay, question is, for node 1, how is it possible that everything can be exiting the node? Okay? So let's actually dig into that a little bit. Is everything exiting the node? Okay? Turns out that, the reason you're saying that is that all the terms look as if they are positive, right? But you have to keep in mind, you've got variables there, the results of which can be negative, right? The variables we plug in there can have negative values stored in them, okay? And so if you look at this, V1 actually came out negative, right? So you don't have a current flowing out of the node in the first term. Because that V1 is negative, that means you got current flowing into the node on that leg.
So are the signs arbitrary then?
The question is, are the signs arbitrary? Okay? And the answer is that, as with many things, yes and no. Okay? You get to choose what direction you are assuming to be positive. That's arbitrary, right? You can either assume exiting is positive and make all of your signs match exiting, right? In other words, when you're writing your equation, you can say, any current that's exiting, I'm going to count as a positive term, okay? Having said that, what that does is it allows you to write everything consistently in your equation, but whether or not things are entering and exiting is going to depend on what your final results say in their signs. Okay? And those will not come out arbitrarily. Those will come out to match the assumption that you made to begin with.
But on the nodal equations,
Yeah.
can you just assume everything is exiting or everything is entering? Would that work?
The question is, can you just, on the nodal equation, assume everything is exiting or everything is entering? And the answer is yes. Now, you'll notice on node 3, I did one where I did not assume something was exiting, right? Look at that last term in node 3. Okay? That one, I couldn't arbitrarily say, oh, that one's, that one's also exiting. Why not? Because I defined it. No, actually, so his comment was, well, is it the polarity of the battery? Not really, actually, because a battery can have a polarity in one direction but have current driven the other direction. So that can happen. The answer is because I wrote it on the figure this way. Once I write it on the figure, I put I2 and show an arrow going the direction that I showed it, I have to be consistent with how I drew it on the figure. That's why I had to put that as a negative down there for I2. Now, it was arbitrary what direction I showed the arrow. Okay? But once I draw the arrow, it's not arbitrary what I put in the equation. Does that make sense? Okay. Good questions. Anything else? Yeah. Okay. So the question is, if it is arbitrary like this, is it important to communicate, especially if it's on an exam or something like that, is it important to communicate what direction you were assuming was positive for different things? And the answer to that question is absolutely. Because your answers, like your boxed numbers with signs in them, right? Like you've numbers with a sign in front of it, those only have meaning with reference to the variables that you defined as you did your process. Okay? So that's an important thing to kind of keep in mind. Turns out, with this nodal analysis thing, we're pretty consistent about how we define all those voltages. So the signs themselves tend to make some sense to a grader, right? Because as long as you did your process correctly and defined a ground node, all of those voltages should be with reference to that ground node, right? And so if you have a negative, that just means it's a lower voltage than the ground node. But still, it's a good idea to have a figure labeled with what you're assuming positive is for all your different parameters that you're using. Those are good questions. Other questions? There is a little bit of a shortcut we can do on that problem. All right? And let me show you the shortcut involves things that we call supernodes. That sounds made up, right? Yeah, I guess it kind of is. We call them supernodes. A supernode is a collection of a few actual nodes, but they are connected by voltage sources. Okay? And what you do is when you do your Kirchhoff's current law equations, you monitor, you kind of evaluate all the entries and exits from that collection of nodes as opposed to just one node. Okay? You want me to show you how that works on this problem? I knew you would. Okay? So let's say I define this ground node again, just like I did on the last one, right? So again, I'll color that one green like this. Now I'm going to have this node up here, just like I did on the last one, but it's connected with this blue node through a voltage source, right? That's what connects the yellow node to the blue node. So here's what you do. You say, all right, I'm going to treat all of that as if it's one giant node. Okay? So all of this plus all of this. Everything in that gray, I'm going to act like that's one node with respect to writing my KCL equations. Okay? Now, when I do that, I don't lose sight of the fact that I do have two different voltages within that node. That can't be done on a real node, right? A real node has all the same voltage everywhere in that node. But when you have a supernode, you can have different voltages at different locations within the supernode. Okay? So the only kind of use that we're using out of doing the supernode is defining a different way of accounting for all my entry currents and exit currents. Okay? So let's do a an equation for that supernode, right? A KCl equation for the supernode. Okay, what I will have there is V1 over 4 kiloohms, right, exiting. Where else do I have flows into or out of the supernode? Will I have a V2 over 3 kiloohms? Right? That's where it exits out of the blue toward the green. I will also have a V2 minus V3 over 1 kiloohm. That's where it goes from the blue over toward the purple. Okay. Any other places where current can enter or exit? V1 minus V3 over 2 kiloohms. Okay. Have I accounted for all the places current can enter or leave? Looks like it to me. All right. And what we do here is we say that all has to be equal to 0. And this is valid, right? If you think about this, you can define, any closed system and say all the currents in and out better sum to 0. Right? So there's nothing in here that allows you to sort of store up that current. It's whatever current, flows in on each one, they still have to sum to 0. Okay? Look at that equation. Does that look like something else that we may have had somewhere earlier? Okay. Now I substituted in this 20 volts. Let's actually look at that real quick. Okay. Does my equation that says V3 has to be equal to 20 volts, does that still apply? So I can still go in here and substitute in for my V3 and make that 20 volts. So that's still okay. What about my other equation that says V2 minus V1 is equal to 50 volts? Okay, those are extra equations that I have. If I take that V2 minus V1 equal 50 volts and combine it with this one down here, that is the exact pair of equations that I solved up here to get that solution. So what we see here is a much shorter, easier method, right, that'll get you the same result. All you have to do is define a supernode. Okay? The other thing I want to emphasize here real quick is it possible for a node to be part of a ground node in a supernode? In other words, is it possible for a supernode to include a ground node? Answer might surprise you. Answer is yes. It is possible for a supernode to include a ground node, right? So it is valid for us to down here take all of this stuff, right, all the way up to here, and treat all of that as if it is like our ground node. Right? Meaning what? Meaning we don't sum currents on it. Right? So we don't sum currents on a ground node. Now we've defined this supernode that's part of the ground, or where ground is a part of the supernode is a better way to say that. Right? So, that means we don't even try to sum currents on that one. And it's okay because we got everything we needed just by summing currents for the other supernode. You like that? Yes, sir. Okay, good question. His question is it possible to chain together, maybe I'm reading into it too much, but I think his question is it possible to chain together multiple voltage sources and create a big ol' supernode? Some people I've heard call that a super duper node. While we're making words up, we may as well, right? Super duper node. Okay? The answer to that question will be answered shortly because we're about to do another example. Two things we're going to do with this example here is answer the question, what about dependent sources? All right? Do these cause us a problem to have dependent sources? And then along the way, we are going to answer his question about, can you chain together multiple voltage sources? Okay? The short answer to his question is, yes, you can. All right? So here's a circuit. It says, define a ground node and find all other node voltages relative to that ground. Okay? As a part of defining how the circuit works, and to try to avoid some confusion, I went ahead and named two of the voltages that I wanted to use with my dependent sources. I named them how I would have named them if I was going through and naming all my voltages anyway. See how I did that? V2 is the voltage across the 10 ohm resistor relative to this. I was going to go ahead and define this as ground down here. Right? So what I essentially did was I showed the voltage at that middle node as being V2, but I showed it with the traditional plus and minus symbol. Right? It's not different, though, because the minus is oriented where the ground is, and so that's the same thing as defining that my V2 is that little crossroads there in between the 10 ohm, the 15 volt, the dependent voltage source up top, and then the 0.5 amp current source right there. Okay? And I did that same thing for the other crossroads here where I've got the two current sources and the two resistors. With me so far? Who's a little scared right now? It's okay to, have a recoiling reaction to what looks like it's going to be a heavy-duty problem. This actually will be kind of a heavy-duty problem, and for that reason, I have decided to show you another way of approaching it using software. Now, it's going to be the same process, right? You're not going to do anything different in terms of having to define the equations, but we're going to do it inside of MathCAD so that once we've written all of them down, it's just another couple of clicks and we'll be able to get answers. Sound good? Here, V1, and this over here is let's call that one V4. Are there any other voltages that I should probably define on this circuit? Are there any other nodes? Let's say that. Are there any other discrete nodes relative to all these that I've just defined? Got my ground node, V1, V2, V3, V4. On those four nodes, are there any other nodes? How about V5 up here? Right? That would be like my fifth node. All right, so there's our circuit we're trying to work from, and I mentioned a second ago we're going to go through and define all the different variables that we are hopefully going to try to solve for. Okay, so let me do V1, and it doesn't matter really what you pick as your initial guess, but you have to pick something. So I'm going to go through and pick initial guesses for V1, V2, V3, V4, V5. Okay, what other variables might I end up with this? I1. Okay, make sure if you're using units, which I am, make sure you define that with the proper units on it. And then I2. Okay, we're going to use a solve block. You start a solve block with the word given. Now, do I have any supernodes? The answer is yes, I do. As a matter of fact, I've got a really supernode, right? Because right here I have two of these voltage sources. One of them is an independent source and one of them is a dependent source, but they chain together right here. So what I can do is define everything that connects to either of those as being one big old supernode, right? So all my inputs and outputs that I have out of that, those two things chained together, I'm going to treat that like it's one big old node. Okay, do I have any other supernodes? Okay, I have another one that's a supernode defined relative to ground down here. Okay, so I tell you what, that might be one of my easiest equations to write right there. What is V4 going to be? What is this dependent source doing? It's holding V4 at 1.5 times V2. Sweet, I got one of my equations. It's not a nodal equation, it's not like a KCL equation, but that's an equation that applies to this system, right? All right, oh, and I used the wrong kind of equal sign right here. Now I've got the right one. Okay, what else? Okay, tell you what, there's no reason in prolonging the misery anymore. Let's go ahead and start doing a nodal equation on this big super duper node. Okay, so what kind of currents do I have exiting that node? I have this dependent current source right here. What does it do? Exits, so I'm going to put 7 over ohms times what? V3. So that's, this is my, I'll put a label up here. This is my super duper node, KCL equation. Okay. 7 over ohms is the first term that I have right there. What do I do next? Okay. Remember, I'm joining up all of this stuff. So it's basically anywhere that current leaves the combination of these two voltage sources. So what's another place where current might leave that? Okay, through the 10 ohm resistor, and that's going to be based on V2 over 10 ohms. Okay. Where else? Okay, there is a 0.5 amps. Is it leaving or entering? Okay, it's leaving, and I'm taking leaving to be positive, so I'm going to say 0.5 amps is leaving right out here. Okay, where else? Okay, 0.2 times I1 is entering up here, right? So I'm going to take that as being minus 0.2 times I1. Okay. With me so far? Anything else? Okay, I have V5 minus V4 over 50 ohms. Or I could just call that what? I2. Let me just call it I2, right? I2 is leaving, so I'll say plus I2. Okay? Any other place that current might be leaving this big super duper node? Usually at this point someone goes, but what do I do about this I1? Yeah, here's the thing about that one. It might exit that node right there. What does it immediately do? Enters back into the same node. So if I wanted to, I could add and subtract I1, but that wouldn't do anything, right? So I'm going to call that a nothing. Okay? So there are all of those terms right there. Control equal 0. That's the KCL equation for the big old super duper node. Okay? Any other KCL equations that I should think about? How about node 3? I defined that with V3, right? So node 3 KCL. What's that equation look like? How about minus 0.5 amps? Right? It's entering, so it's minus 0.5 amps. What else? Okay. So we have 0.2 times I1 that's leaving, so I take plus 0.2 times I1. Then what? Plus V3 over 20 ohms, right? That's how much leaves going from 3 back down to the ground node right there. Then what? Plus V3 minus V4 over 30 ohms. Okay, it looks to me like there are 4 paths into and out of that into and out of that node, and so we've got 4 terms there. Looks like we're probably in good shape. Okay, so the answer to that is, do we need to define V4 since it's connected to the ground node? And in a sense, I kind of have done that because I know how this dependent source right here behaves. It's going to have a voltage that's going to be 1.5 times V2. Right? V2 being right here. This is going to be 1.5 times V2. So I can leave V4 as a variable and define its behavior with one of my equations. Okay? All right. So let's take stock real quick. How many unknowns do I have so far in my system of equations? Looks like I've got V3, V2, I1, I2, V4. Okay. That's 5. I've got how many equations? Not quite there yet, right? What do I need to do? Have I used all my relationships yet? Okay. For instance, is there some kind of a relationship I can define for how this dependent voltage source right here works? In other words, maybe it could be something like this. V2 minus V5 will be what? 6 ohms times I2. Now, I did that one. It looks like before now I may not have had anything going on with V5, and now I do. So I added another equation, added another unknown. Shucks. Where else can I look for certain relationships here? me ask you this. Is there a relationship between V2 and V1? Okay. Yeah, V1 minus V2 is equal to 15 volts. Now you might go, okay, did that help us at all? I just added an equation, but I also added one more unknown. We didn't have V1 in there before, right? Let's keep digging, okay? What do you think I should try to do next as far as another relationship? Okay, we've mentioned this one already, but remember when I put 2 in right down here? Someone had a suggestion for something to put in there instead of I2. What is I2? Okay, it's going to be equal to V5 minus V4 over what? 50 ohms. Okay, now are we getting somewhere? Okay, maybe, maybe not. All right, what's our current count? It looks to me like we have all our voltages in there now, right? V1, V2, V3, V4, plus I1, plus I2. All those variables are included in some equation somewhere, at least, in my system. That's 7 unknowns. How many equations do I currently have? Okay. Any other relationships I can pull out? Do the same thing for I1. Okay. I1, how is it working? Okay. V5 minus V1 over 40 ohms. I now have 7 equations, and I have 7 unknowns. Are we ready to go for broke here? Okay. The way you want to do this, since I'm doing all these with units, it's important when you do this and you're about to try to solve this, it doesn't like it if you have mismatched units in your variables and you just do like find equals. Okay? In MathCAD, what you want to do if you have that scenario is you want to insert a matrix first and then put the names of all your variables you're trying to solve for, right? V1, V2, V3, V4, V5, I1, and I2. And then say find, and then name all those again, right? V1, same order, V2 with commas, V3, V4, oops, V5, I1, and I2. Okay. And if you get the little green squigglies like this, at least in MathCAD 15, that's a good sign. Right? It means it probably solved it. So let's see what we've got for some of these things. V1, 3.549 volts. V2, negative 11.451 volts. V3, 0.66 volts. Okay, V4, negative 17.176 volts. V5, negative 12.64 volts. Okay, what about I1? All right, I1 is negative 0.39 amps, and I2, 0.102 amps. Because I'm a good engineer, I like boxing my answers. I hope I'm a good engineer. That one looked scary at the beginning, didn't it? What did we do, though? Start breaking it down. You try to identify your supernodes. Do your KCl equations on your supernodes, if it's not part of the ground at least, right? Do your KCl equations on regular nodes also. That'll give you a certain number of KCl kind of equations. If you have dependent sources especially, a lot of times that will not be enough to just have those. So what do you do instead? You bring in these extra relationships that are defined with either independent or dependent sources can cause there to be relationships that you bring in as far as the extra ones. Those will typically come in and fill in the gaps and allow you to find not only the variables that you were asked for, but sometimes you find some extra ones along the way as well. You like that?